Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We are on chapter 15, the phosphorus cycle. And more specifically, today we will be looking at phosphorus cycling in the epilimnion. Nutrients released by zooplankton are rapidly reassimilated by phytoplankton. Under certain circumstances, when the concentrations of phosphorus in the trophogenic zone are low, phosphorus and nitrogen regenerated by the herbivorous zooplankton can constitute a significant portion of the phosphorus and nitrogen requirements of the algae. For example, based on nutrient budget and in situ measurements, epilimnictic zooplankton in Lake Washington recycled 10 times more phosphorus and 3 times more nitrogen to the surface mixed layer during the summer months than enters from all external sources combined. Examples of the rates of regeneration of phosphate and ammonia by zooplankton are given in table 15-11. The magnitude of nutrient uptake and recycling depends on the nutritional status of the algal cells. Compared with nutrient-sufficient cells, nutrient-deficient algal cells assimilated phosphate and ammonia more rapidly and exhibited lower rates of remineralization. Zooplankton grazing accelerates rates of phosphorus and nitrogen regeneration. It is also probable that planktonic bacteria, particularly those less than 1 micrometer in size and very small algae, immediately sequester released phosphorus. Even though average phosphorus and often combined nitrogen concentration in the epilimnion can be low, the release of nutrients from zooplankton can cause a macro-heterogeneous patchiness of nutrient concentrations. Since the zooplankton distribution is far more clumped than the phytoplankton distribution. Less clear is the importance of nutrient recycling to the overall rates of algal productivity on an annual basis. Removal of algae and bacteria by grazing zooplankton fluctuates widely on a seasonal and spatial basis. Moreover, grazing of algae is often selective, site-selective that is. This selectivity may enhance the availability of nutrients to those algae that are not as effectively grazed. For example, assimilation rates of phosphorus by various dissolved and particulate fractions and different zooplankton species were examined in a mesotrophic lake. The micro-consumers less than 20 micrometers exhibited the largest specific phosphorus assimilation, 0.28 per day, and regenerated about 45% of assimilated phosphorus. The larger microcrustaceans, such as Daphnia, acted largely as sink for phosphorus, whereas the cyclopods regenerated rapidly the small amounts of phosphorus assimilated because of their active feeding on the macro-consumers. The zooplankton contributed significantly to the sedimentation of phosphorus at this time of the year. The interaction are furthermore complicated by seasonal patterns of selective predation on zooplankton by planktivorous fishes. As indicated in chapter 22, planktivorous predation often results in reductions in zooplankton size and therefore grazing rates on phytoplankton. The smaller zooplankton can have higher biomass-specific excretion rates of phosphorus than larger zooplankton, although fish excretion of phosphorus is large per unit biomass. The collective biomass is very small. In other studies, rates of phosphorus release from pelagic zooplanktons were reduced during June and July when fish predation reached its seasonal maximum and allochthonous supplies were at seasonal lows. So before we move on, let's look at this table here, table 15-11, regeneration rates of ammonium-based nitrogen and phosphate-based phosphorus by some freshwater zooplankton. So on the left, we have the species of zooplankton. Here we have their temperature range for viability, I believe. This is the micrograms dry weight per animal. So this is the mass of the species of zooplankton. This is the in micrograms, this is the milligram dry weight per day of nitrogen and phosphorus, and then this is the source of where that data was taken from. So we have, let's see here, so the one with the highest mass would be this Daphnia longispina. We have a total dry weight of between 200 and 250 micrograms. And we don't have any data for nitrogen, but phosphorus we have 3.4. Then we have a range of temperature here, where they are viable, where they can live at. So for example, we have colder species, so they live in areas that could be as cold as 5 degrees centigrade and as warm as 20 degrees centigrade for copepoidas, and their dry weight is 3.6 or 2.9 micrograms. And they don't have any data for nitrogen, but they have data for phosphorus, and it's 1.9 and a higher mass for the warmer species at 6.0 micrograms. And then we have different cladoceras here, and their location within the lake. So the epilimnion compared to the hypolimnion. And then we have mixed epilimnetic zooplankton. And so that is pretty much like a mix of those type of zooplankton, and therefore their temperature range is in this range here. And there is actually data for both nitrogen and phosphorus, so pretty high range, especially for nitrogen. For those zooplankton that live at temperatures less than 15 degrees centigrade. We have nitrogen ranging between 0 and 85 micrograms, and then we have phosphorus also a pretty good range between 6 and 55 micrograms. Finally, it must be recalled that most of the phosphorus is bound in particulate matter, algae, bacteria, and detritus. Rates of nutrient regeneration from these sources, as the phytoplankton senesce and die, are properly understood. Certainly, these organisms with short generation times rapidly recycle nutrients in the trophogenic zone before they settle to lower depth. The relative magnitude of their recycling to that of the zooplankton is not clear, but is variable spatially, seasonally, and diurnally, and is probably affected by mean depth with greater recycling within the water column in deeper lakes. Zooplankton grazing and concomitant nutrient recycling can enhance rates of primary productivity and algal growth during periods when heavy nutrient demands exceed loading inputs to the trophogenic zone from external sources. Nearshore nutrients shunt. Even in large lakes, dense inshore population of benthic filter feeders can redirect nutrients in particulate form and energy away from offshore pelagic zones to inshore sediments. Invasive dreissennate mussels appear to be responsible for the higher content of nutrients and organic matter in nearshore sediments compared to offshore in Lake Erie. Dreissennate filtering rates were high enough to lower mean ice-free chlorophyll A concentration, increase Secchi depth, and increase minimum volumetric hypolimnetic dissolved oxygen concentration in Lake Erie and Lake Simcoe. Hecke et al. Conclude that dreissennates have not only substantially modified the inshore physical habitat, but their ecological activities may have also changed the availability of resources to other species at the ecosystem scale. Phytoplankton requirements for phosphorus. Compounds containing phosphorus influence nearly all phases of metabolism, particularly in the energy transformation of phosphorylation reactions during photosynthesis and respiration. Phosphorus is required in the synthesis of nucleotides, phospholipids, sugar phosphates, and other phosphorylated intermediate compounds. Further, phosphate is bounded usually as an ester in a number of low molecular weight enzymes and vitamins essential to algal metabolism. The importance of phosphorus in phytoplankton physiology is of special interest to the limnologists because phosphorus is the least abundant element of the major nutrients required for algal growth in a large majority of freshwaters. Furthermore, the most important form of phosphorus for plant nutrition is ionized inorganic phosphate, or orthophosphate. Although phytoplankton can utilize organic phosphate esters, such as glycerophosphates, this ability is variable among species, as is their ability to obtain phosphate groups enzymatically or by the release of exoenzymes to the water for catalytic dissociation. Most phosphorus released to the water during the active growth of phytoplankton is inorganic soluble phosphate and organic esters, which are in turn very rapidly recycled. During cell lysis and decomposition, most of this phosphorus released by the phytoplankton is organic and undergoes bacterial degradation. Phosphorus concentration required for growth and uptake. Phosphorus transport uptake across the outer cell membrane generally follows Michaelis-Menten enzyme kinetics, while the phosphorus uptake rate, V, versus extracellular concentration, S, curve is described by a rectangular hyperbola. So V is equal to Vmax divided by Km plus S, where Km is a half saturation constant defined as the concentration where uptake is half its maximum uptake rate Vmax. The initial slope of phosphorus uptake rate versus extracellular concentration, defined as Vmax over Km, is an indicator of the relative competitive ability of a species to acquire phosphorus at very low concentrations. The half saturation constant alone is not an indicator of competitive ability at low phosphorus, although it is sometimes used as such. At steady state, population growth rate versus substrate concentration also follows a rectangular hyperbola, and kinetic equations similar to uptake equation can be used. Cyanobacteria appear to have higher phosphate uptake affinities than eukaryotic algae and hence would have a competitive advantage at low phosphate concentration unless limited by something other than phosphate uptake and light. The uptake of phosphate from the water is influenced by numerous external factors. Among many phytoplankton studied in culture, the initial absorption of phosphate and subsequent uptake increase with light intensity and are also affected by spectral quality. Natural populations are more or less synchronized by daily photoperiods in their productive and growth cycles, and protein synthesis predominates in the initial portion of the daily light cycle. In the green algae Senidesmus, the release of phosphate from the algae has been found to be greatest during the later portion of the light period, both prior to and during cell division in the dark. Absorption of phosphate per cell in the light is generally dependent on phosphorus concentration in the medium, within a range that is rather specific for a given algal species. Natural phytoplankton and bacterial populations, however, adapt to phosphorus-limited environments by synthesizing enzymatic transport systems capable of uptake at very low concentrations. Uptake by phosphorus-deficient cells in the dark is dependent on phosphate concentrations. When phosphate is supplied in excess, phosphorus is often incorporated and stored as polyphosphates. Nitrogen and carbon limitation can lead to intensive polyphosphate production, and such phosphate accumulation is simulated by calcium. When phosphate concentration become limiting, production of the polyphosphate forming enzyme polyphosphate kinase decreases and the phosphate stores can be degraded in the light. Phosphorus uptake rates are quite specific to groups of phytoplanktons and often to species within a genus, whereas nitrate uptake is independent of phosphate concentration. Optimal growth of many phytoplanktons occurs at higher concentrations of phosphate when nitrate rather than ammonia is the nitrogen source. Phosphate uptake and transport through the cell membrane, the rate-limiting step by cyanobacteria, is strongly regulated by cation concentration, particularly Ca2+ and Mg2+. Thus, phosphate uptake by cyanobacteria should be favored in hot water with an abundance of divalent cations unless the cyanobacteria are limited by another nutrient. However, cyanobacteria may dominate soft water eutrophic lakes, so low cation concentration are not necessarily detrimental to their dominance. Studies of growth of the natural phytoplankton communities under gradients of nutrients indicated that diatoms were superior competitors for phosphorus and dominated at high silica to phosphorus ratios, that is, when silica did not limit diatom growth, then at green algae, whereas green algae dominated at low silicon to phosphorus ratios because they were superior acquirers of phosphorus under the experimental conditions. This is an example of resource competition theory, which states that the species with a significantly lower resource requirement is the superior competitor when they are limited by the same resource. Species will coexist only if each is limited by a different resource, or if the species are limited by the same resource and do not differ significantly in their resource requirements. This theory explains how competition for limited resource leads to a species becoming dominant within a phytoplankton community in a natural system under a given set of conditions, light, pH, hardness, etc., in the absence of chemical warfare. This theory explains how competition for limiting resource leads to a species becoming dominant within a phytoplankton community in a natural system under a given set of conditions, light, pH, hardness, in the absence of chemical warfare, allelopathy. Phosphate uptake and pH. Many species of phytoplankton exhibit optimal growth and uptake of phosphorus within a distinct range of pH of the medium. Changes in the medium pH can affect a variety of metabolic activities, which may include altering rates of phosphate absorption by direct effects on the activity of enzymes and on the permeability of the cell membrane, or by changing the degree of phosphate ionization. For example, the uptake of phosphorus by the diatom Astarionella is greatest at pH values between 6 and 7. Uptake rates of phosphorus have been correlated directly with the presence of numerous ions and compounds in the water, such as potassium, availability of macronutrients, and organic compounds. The mechanisms involved are not clearly understood. Phosphorus concentration required for growth. Growth rates of algae and cyanobacteria in both natural and laboratory cultures exhibit dependency on the amount of available phosphorus and the rate at which it is cycled between cells. Extensive investigation of minimal and maximal phosphorus concentration, especially by Chu and Rudd, grouped freshwater algae into categories according to whether their tolerance ranges fell below, around, or above 20 micrograms of phosphorus per liter. A species whose optimum growth and upper tolerance limit is below 20 micrograms of phosphorus, and some species of the macroalgae Chara. B species whose optimum growth is below 20 micrograms of phosphorus per liter, but whose tolerance limit is well above that level, for example, Astarionella and other diatoms. C species whose optimal growth and upper tolerance limit is above 20 micrograms of phosphorus, for example, green algae such as Cinedesmus or Enchistrodesmus, and many others. In these studies, phosphorus concentrations of the culture media required for optimal growth were almost always higher than those of the water in natural habitats where the algae were growing. Many explanations were offered for this difference, such as the presence of unknown organic growth factors in the lake, but not in the artificial media of the bacteria-free cultures. It is now apparent that the chemical mass of inorganic phosphate in the water is not the only factor affecting growth kinetics. Of overriding importance is the rapidity with which phosphorus is cycled and exchanged between the particulate phosphorus and soluble inorganic and organic phases, as discussed in detail earlier. Secondly, it is of great ecological importance that many algae and cyanobacteria, when provided with a sufficient supply of phosphorus, can absorb phosphorus in quantities far in excess of their actual needs. A portion of this phosphorus is lost in normal active growth, both as inorganic and organic compounds, and is recycled rapidly, at least in part. A large majority, greater than 95% of the phosphorus, is in the particulate phase of algae and dead organic cestine in phosphorus limited system, but is lower in nitrogen limited eutrophic systems. Assimilation of surplus amount of phosphorus by algae, often referred to as luxury consumption, can provide sufficient phosphorus to sustain algal growth in the epidemion as the external concentration of phosphorus becomes very low. And that is it for today, and thank you for chiming in, and I'll see you tomorrow. Bye.